Right then, this is question 7. It says a measuring cylinder has a radius of 3 centimeters. Let's just draw what we've got. So let's make it all fat and dumpy so it all stands out nicely. That is a thick measuring cylinder. It looks more like a beaker, but you can forgive me, yeah? So there we go. We have a radius of 3 centimeters. Let's put it in black so it stands out. So we have a radius there, R equals 3 cm. And it contains water to a depth of 10 centimeters. So just put the water in blue, since we've got a seaside theme. So here we are, there's the water there. So from there to there we have a height of 10 centimeters. Now I'm going to drop a small ball bearing, I assume it's a ball bearing, yeah, it's a sphere, into the cylinder. So I'm going to plonk it in there, and the water level will rise by 2 centimeters. So let me just draw a little red ball bearing sitting there. So there it is, all sitting there looking happy with itself, and I just went plonk it in there, and there it goes. There's my little ball that was outside. I'm going to throw it in there, and that is my metal sphere. And I just shoved it in the water. Now the water level is going to rise by 2 centimeters. So by the time my red ball has gone in there, I've now gone from there to there, which is obviously 12 centimeters. Isn't that right? I don't need to know that it's 12, but clearly if it's gone up by 2, then the depth of water in the measuring cylinder is going to be 12 centimeters. So guess what? The key thing is my height rise equals 2 centimeters, and that's the most important part. It says, what is the radius of the sphere? Well, we know the formula for the volume of the sphere is going to be 4 thirds pi r cubed. So if I want to work out the radius of the sphere, I need to work out the volume of the sphere first. Now the volume of the sphere is related to the height at which the water level was raised when I threw the sphere in there. So in other words, this little sphere takes up this amount of volume inside the cylinder. So imagine that little portion of water there. That is due to the sphere being chucked in there. So essentially I can work out the volume of my sphere not using this formula here, but in fact by working out the volume by the rise in the water level caused by the sphere. And of course you know the volume for a cylinder is V equals pi r squared h, and I'm not going to use the whole height. I'm going to use 3.14 because that's pi. I know the radius of this cylinder into which the sphere was dropped is 3, so it'll be 3 squared, and I'm going to multiply not by 10 or by 12 but just by 2, because that was the rise due to the cylinder going in, the sphere being dropped into the cylinder. So pi times radius squared times a height of 2. Alright, I grabbed my machine earlier. I made that 56.52 centimeters cubed worth of volume due to the sphere. Alright, they're related now. Right, so if I now know my volume of the sphere is 56.52 centimeters, I can then substitute into this formula here and get my radius in the normal way. So let's just go back to yellow then. So I've got 4 thirds times pi times radius cubed, which is still unknown, comes to 56.52. Alright, so I merely used the 56.52 and shoved it in there because it's the same volume. Okay, so I could work this little bit out. Listen, I can't bother to do that. If I'm dividing by 3, take it over and multiply it. So I go 3.14 times radius cubed equals 3 lots of 56.52. And while we're at it, since I'm multiplying by 4, I may as well take it over and divide by 4 in one step. Right? So the 3's gone up, gets multiplied, the 4 goes down, gets divided. And I've got a step for that. That came to 42.39. And so to get the radius cubed by himself, you take your 42.39 and simply divide through by pi, which is the 3.14. That gave me an intermediary answer of 13.5 pretty much. So to get the radius on its own, you simply cube root the 13.5, and that left me with 2.4 centimeters, because I did it earlier and I know it's right. Okay, a very nifty little sum. Amongst the A-star questions, I don't really think that's A-star, it's very straightforward really. Just need to be able to see what's happening here in the storyline. Again, if in an exam you may be drawn a picture, but if not, I'm going to say draw a little picture so you can see what you're doing. Otherwise you might accidentally use the H, the 10 for the height, or the 12 for the height, but not the 2. If you draw a little picture, then the chances are you're going to use the correct height in the right place to get the volume of the sphere. And that's it. Now I want to do question 8 as well in this one video. This is not only A star, it's gone off the A star scale, and it's got one of these little horrible yellow triangles with a red exclamation mark in it, like danger, watch out, it's really hard. It's not, it's just a bit tricky. So this is question 8 then. A semicircular piece of card with radius 10 centimeters is curved to make a cone. Standard question. What's the volume of the cone? Seems ever so easy. All I've got is one number to deal with, and I've got to work out one thing only. These are always a lot harder than they look, but anyway. Semicircular piece of card. So here's my semicircle, drawn nice and big. I know if I put that as the center there, then I know my radius from here to here is going to be 10 centimeters. Alright? And I'm going to make a cone, so let's just quickly construct a cone. And here's my cone, looking a bit like that. The rest has to go freehand. So there's your circular base there, and there's me looking through the card with my X-ray vision just to see what's happening there. Volume of the cone. Now let's just recall the formula of the volume of the cone lest we forget it. So volume of the cone then, here we go. I know that V equals 1/3 pi times radius squared times h. So I know I'm going to be using that sometime. And the trouble is, this is the radius of the cone. So it's a different radius to the radius of that semicircle. Now, let's just work something out. You need to be able to visualize that if I take this straight edge and that straight edge and fold it onto itself, this part will form the circular base of the cone. If you can't see it, draw a semicircle accurately on a piece of paper, cut it out, fold it at that point there, and make these two edges join because they're equal in length. When they form two edges that join, you get this part of the cone, and this circular part here, this circular arc, semicircular arc in fact, will become the full circumference of the entire circular base. Therefore I need to know the length of that arc there. So let's just do it straight away. Well, I know circumference equals 2 pi r, but I'm working with a semicircle. Therefore arc length is simply 2 pi r divided by 2, doink doink, in other words pi times radius. So that's going to be 3.14 times 10, guess what, I've got 31.4 centimeter radius. Now I can transfer that over to here because I now know, sorry, 31.4 arc length, not radius. So I now know that this 31.4 is in fact the full circumference of this circular base for the cone. So I know that again here, C equals 2 pi r, but 2 pi r equals a numerical value now. It's 31.4 centimeters. So the radius is going to be 31.4 divided by 2 lots of pi. 2 lots of 3.14, 6.28. If you work that out, you get a radius of pretty much 5 centimeters. Spot on, near enough. Alright, so that's good enough. So the radius is 5. I will now write it in. So r equals 5 centimeters. Now, next step, I need to work out the height of this cone. So let's just draw it in red so it stands out really nicely. There it is. So this is the punch line. I want to know what height it's going to be. So there's an H there. Now, very carefully, if you just recall that this side and this side are identical because they're both radii through the center there, then if that side matches that side and this folds to produce this lovely cone here, then the radius is in fact identical to the slanted side that we will produce. So here the slanted length is also going to be 10 centimeters. Now again, I'll underline that so it stands out really well. So I've got an H, a 10 and a 5. Now all there is for me to do now is to work out the height of the cone using Pythagoras and substitute my value into there, and hey presto, we've got the volume of the cone. Okay, so it's a bit fiddly getting there, so let's just do a bit of maths down here then. So what have I got here? I've got the height squared plus my radius squared makes my length squared. Alright, h squared plus 5 squared, 10 squared. And working backwards, I've got h is going to be 10 squared, take away the 5 squared, and then you square root it. Again, this is, you know, A star and beyond, so you don't need to show all these little steps. You just jump straight into that if you want to. Use your machine and you will eventually get 8.7 centimeters. So the height is therefore 8.7 centimeters. Since it was in blue, I'll underline it in blue like that. Alright, so the height is 8.7 centimeters. And now the final part, let's just work out the volume of the cone. Now re-quote the formula. Again, no marks in the exam for doing this, but since I'm teaching it live now, it's good to show fully what's going on. So a third times 3.14 times a radius of 5, there it is, radius of 5, so it's 5 squared, multiplied by the height we've calculated, 8.7. Punch it into the machine, you go 3.14 times 5 squared times 8.7, then divide by 3, you will get what I got, I hope. I got 227.65 centimeters cubed, so let's just call that roughly 228 centimeters cubed, and justify it by saying 3 significant figures. I think this exercise is about 3 significant figures. It says give your answers correct to 3SF unless they work out exactly. Well, it doesn't work out exactly, so that's good enough. Either of these two would be fine. But anyway, isn't that lovely? Semicircular piece of card with just one number, radius is 10. Now work out the volume of the cone you can make with it. Amazing, isn't it? So, well, there it is. That's all the working. Study the video. It's really, really nice. It's really interesting. And enjoy the background. It's a lovely sunny day there in Weymouth, and I trust you're having one too as well. Okay, so catch you later for more questions.